Jai Hind. In this video, we are going to discuss the introduction of finite automata. Okay, so if we are going to discuss the finite automata, let's say finite automata, when we are going to discuss the languages, and we are going to discuss the definition, the formal definition of DFA. Then we are going to discuss how we are going to represent those automata. So whenever we are going to discuss this languages or the finite automata, there are some things we should know about, like the alphabets. Okay, so when we talk about the alphabets, alphabet is any finite set of symbols. Okay, so every time if we are using, we are going to use a certain string, so that string must be a collection of certain symbols, and those symbols belong to certain set. Okay, so that set is known as the alphabet. So we can take the examples like this ASCII encoding. It is having let's say 127 characters. So it is these all are the sets of certain symbols. Then Unicode. So this encoding is also, we can just categorize it as alphabet, and we are having this 0, 1 binary alphabets and ABC. So these all are the examples of alphabets. Now strings. Now whenever we talk about the alphabets, we can make certain string by just combining some certain alphabets, and those alphabets must be from the those strings or those symbols must be from the alphabet set. Okay, so for example, we are having certain one second. Suppose we are having certain alphabet set that is containing 0 and 1. Now we can make a certain string by combining by the combination of, or we can say the repetitive combination of these 0 and 1. So let's say I am going to write certain sequence of this 0 and 1. So we are having here 0 1 0 1 1 0. So this is a string. So what we are doing, we are just combining certain symbols to create a string. So these are certain examples of a string. So just take a look at this particular symbol here. So this 0 1 star, this 0 1 star, it is just representing the clean closure. So whenever we are having 0 1 star over any input alphabet, or it may be input alphabet or it may be output alphabet, in general it is an alphabet. So it will create a set of all possible combinations of these symbols which are available in this alphabet. So we are having this epsilon. Epsilon is representing the empty string. So we are not having any symbol in it. So if we are talking about this 0 and this 1. Now just take a look here, we are having 0 and 1. So this 0 and 1 individually, it is a symbol in this alphabet set. Now what we are having here, this 0 is representing a string, and we can say that this string is having length 1, and there are many combinations possible. Then the deterministic finite automata. Now deterministic finite automata, or generally each if we are talking about any kind of automata, these we are just using those automata to process a certain string. Now in this DFA, if we are going to discuss the formal definition of it, this DFA is having certain tuples. So we can say that it is having a finite set of states, and we are representing this finite set of states by Q, and it is having input alphabet which is representing by this sigma, and a transition function which is representing by this del, and Q0, it is your start state, or we sometimes say it as initial state, and set of final states. So in DFA, we can conclude from here that there must be only one initial state, and from this statement we can conclude that we can have more than one final state, and alternatively we can use the final or accepting state for this final states. Now the transition function is very important thing in this DFA, because whatever the transition we are doing, whatever the states we are just whatever the next state we are going to process, that will be defined by this transition function. So when we talk about this transition function, we are representing this transition function like del QA. It is taking two parameters, the one is Q and another is A. So this Q is representing the state that the DFA goes to when. So this Q, we can say that this is the current state, okay, and this A, it is the input we are going to process, and the result of this, or we can say this, the whole value of this del QA, it will be the state the DFA is reaching after just reading this input A. Now we are having certain representations of DFA. We can represent in certain ways the DFA. We can represent it as a graph, or we can represent it as a table. So in this graph representation of DFA, what we are having nodes, and nodes are representing the states, and there are certain arcs, and these arcs are labeled arcs, and they are just representing the transition function. So if we are having a state P, and let's say we are having this state P, and we are having this state Q, and there is an arc from state P to Q. So in this case, there will be certain input symbols. So if we are going from P to Q, there must be certain input which we are reading at state P. So this input will be labeled on this arc, okay. So we can see that by this representation, what we are having that it at P we are reading input to 1, and after that we are changing to state Q. So we can represent this statement like del P1 is equals to Q. So, and there is one more thing, that the start states, whatever the start state in our DFA is, we are just putting an arrow at that start state, and that arrow or that arc is labeled by start, okay. Now final states are represented by double circle. So if I am drawing a double circle here, so we can say in this representation, this P is our start state and this Q is our final state. Now what we are generally doing on the DFA is, we are going to accept certain string on a certain DFA. We are going to check whether a particular string is accepting or not, okay. So just take an example of this DFA. So this DFA accepts all strings without two consecutive ones, okay. So if we are having certain string like 101, so you can see that in this string we are not having two consecutive ones. So if we are having 0110, then in this string we are having two consecutive ones. So this DFA will not accept any string which is having two consecutive ones. So you can say that this will not be accepted, and this string will be accepted. So let's take a look here how we are going to do that. So A and B, these are the final states, and A is the start state. So every time we are going to read the input, we are going to start from this initial state, and at the first point we will read certain input value on this A, and that may be 0 or 1. So if we are reading 1, then we will move to B. If we are reading 0, then we are going to move to A itself. So at B, if we are reading 1, then we are going to a certain state from which we are not coming back, okay. So and if we are reading 0, then it is moving to state A. So in this case, if we are having two consecutive ones, so suppose we are reading 1 at A and then we are reading 1 at B, so we are reading two consecutive ones, then we are reaching at certain state, and this state, as you can see that we are not having any transition from this state to any of the final state. So we will not come back from this state, okay. So in DFA, what we call this state as, we also call this state as a trap state. So we are trapped here, okay. So this is a simple example of a DFA. Now there is another representation, that is table representation. So in this table representation, what we are having? We are having rows, and those rows are representing the states. So this A is a state, this B is a state, and this C is a state. Then we are having columns. The columns are representing the input symbols. So the first column is, this is for 0 and this is for 1. And then in this table representation, we are representing the final states by putting a star. So all the starred states are final states. So here A is a final state and C is a final state. And then we are putting an arrow for the start state. So this A is a start state. Now the transition function. So we can just extend that transition function, and the extension of transition function means that we are just, let's suppose we are processing, we are having a transition function at Q for input A, okay, and if we are putting here a string which is having more than one symbol, okay, so that transition function is in certain books or certain study materials, this is represented as extended transition function, okay. So we can take a look here that there are two things we have to follow in these transition functions. The first thing is del of Q over epsilon is equals to Q. So if we are reading any input symbol, or we can say we are not reading anything, or we are reading any empty string, then the state will not change, okay. So let us going to the previous example. So if we are at this example, and suppose we are at state A and we are not reading anything, where do we go? So there is nowhere to go, okay. So we will remain at state A. So that is the basic condition for the transition function. Now another thing, that del Q W A is equals to del of Q W A. So we are going to find out what will be the state when we are going to process that del Q A. So that state will be defined by first processing this del Q W, and after getting the state for this, we are going to process that state on this input A, okay. So suppose we are having certain symbol here, that let us say in certain automata, we are just taking an example here. If we are going to process 101, then we are having an output, let's say P, okay. Then if we are going to process this 1010, in that case what we will have, first we have to process this Q on 101. So we will get the final state as del of Q 101, and now this is the additional input symbol. So we are representing this input symbol by A in our definition. So we will have 0 here. So the state for this transition function we are getting is P. So we are going to read this input P, this input 0 on this state P, then whatever the state we are going to, whatever state we are reaching at, that will be the output. Now there are certain conventions we generally follow, that we represent that W, X and Y. So we use these kind of symbols for the strings, and we generally use A, B, C for single symbols in our examples, okay. So now that extended transition function or the extended delta. So suppose we are having this table here, and in this we are going to find out what will be the next state when we are going to process this 011 on B, okay. So for that, first what we have to do, we have to process this B for 01, and later we will process the output of this for 1, and this B01, this 01 is also having more than one symbol. So first we have to just find out whatever is the next state for del B0. So from here we can see that if at B we are reading 0, the next state is A. So from here we are getting A. Okay. Now at A, if we are reading 1, the next state will be B. So we are getting B here. And now at B, if we are reading input 1, what will be the next state? That is C. So at B we are reading 1, then the next state is C. So now there is a representation delta hat. In certain books or in certain references, you will find out that we represent that extension of delta or extension of transition function by putting a certain hat on this delta. Okay, so we can represent the extension of delta or transition function as delta by putting a hat on that delta, and in certain books it is represented like delta star. Okay, but it is not necessary actually. Okay, so because this del is doing the same thing as we are this delta is doing, but to make a certain difference, so we can just identify that this is a particular transition function is for a single input symbol, or a particular transition function is for a certain string, then we generally use. Now the language of DFA. So there, if a certain string is accepted by a DFA, then we generally say that the language is the string is accepted by a DFA if it reaches to the final state. So suppose we are just processing a certain string and we are starting from the initial state and then we are reaching at the final state, then we say that the particular string is accepted. Now if we are having certain set of strings and those set of strings are accepted on a certain DFA, and those set of strings are just generated from certain pattern, then we say we generally create a language out of those set of strings. So that language is a set of strings. Okay, and if those set of strings are accepted on this DFA A, then we say that this LA is accepted on this DFA. Okay, so and accepting means that every time we are reaching at the final state. So there is a path, there is a labeling path from the start state to the final state. So just taking this example here, and we are going to find out whether this string 101 is acceptable by this DFA or not. Okay, so we are starting at A, and by starting at A, first we are reading this input 1. So we are just following this arc which is labeled by 1. Okay, then by just following this arc, we will reach from state A to B. Then we are following the arc from the B for input 0. Okay, so we are just following this arc which is labeled by 0, and then we are following the arc which is labeled by 1 from the current state A. So in this previous transition, the current state was B and the next state was A, and in this transition the current state is A and the next state is B. Okay, so for this input, this string 101, first we moved from A to B, then from B to A, then from A to B. So we can write it down as, first we are moving from A to B and the input was 1, then we are moving from B to A, the input was 0, and again we are moving from A to B, the input is 1, and this B is a final state. So we are starting from the start state and we are reaching at the final state. So we can say that this string is in the language, or this string is acceptable by the DFA. Okay, so here for this example we can conclude that it will accept all the strings W such that W is in 0 1 star. Now we have seen that what is the meaning of this 0 1 star, and W does not have two consecutive ones. So again, we are not having the two consecutive ones. So if we are having certain strings like 0 1 1 0, so this automata will not accept that string. Or if we are having 1 1, so every string which is having this kind of sequence in it, at every position or any position, then that particular string will not be accepted by this DFA. So this DFA will not accept such kind of strings. So this is it from this lecture, and in next lecture we are going to discuss the NFA, non-deterministic finite automata. Thank you.